There's an enrichment challenge in the 2019 Cambridge textbook for Year 11 Mathematics Extension, which I found quite interesting. The first part of the problem asks us to factorise a cubic polynomial using long division. Now, this requires care, but it's fairly plain sailing. Our first move is to multiply the divisor x minus 1 by x squared. This gives us x cubed minus x squared. Subtracting that from the dividend gives a remainder of x squared minus kx. Next, we multiply the divisor by x, and that gives us x squared minus x. And subtracting this from the dividend gives us x minus kx. Factorising the remainder gives us 1 minus k into x. So 1 minus k is what we multiply our divisor by again. And this gives us 1 minus kx plus k minus 1. And subtracting gives a remainder of 12 over x minus 1. So we have x cubed minus kx plus k plus 11 divided by x minus 1 equals x squared plus x plus 1 minus k plus a remainder of 12 over x minus 1. And if we set all of this to 0, we have x squared plus x plus 1 minus k plus a remainder of 12 over x minus 1 equals 0. Obviously, we now rearrange this equation into an expression with k as the subject. If we add k to both sides and switch the equation around, we're there in one move. That's the first part of the question done. Part 2, I found a lot more work cognitively. Cambridge offers a worked solution, but it didn't immediately make sense to me. So here's how I solved it with help from friends. We're asked to find values of k that give the initial cubic equation an x solution which is both positive and integer. Additionally, we're asked to find values of k for which the equation has at least one positive integer solution for x. Why at least one? Well, if we examine a graph of y equals x cubed minus kx plus k plus 11, we see, of course, that it is a cubic. And as we change k, the value of x that makes the equation equal 0, that is to say, that is a solution to the equation, changes. But that's not all. For negative values of k, there seems to be only one value of x that's a solution to the equation for any given k. But once we hit a k value of 17 or so, we can see that there will be two solutions, and the second one is positive. To be precise, there's going to be 3 solutions, but the 2 positive ones are the same. Once k increases beyond that, there are 3 distinct solutions, and 2 of them are positive. So now we understand why the question stipulates that the equation has at least one positive solution for x. Moreover, we know from a visual analysis that the minimum value for k for this to occur is going to be 18 or so. But there's more. Because k can increase or decrease in infinitely small amounts, it follows that the x solution will also change in infinitely small amounts. And what that means is that there will be infinitely many x solutions, but only some of them will be integers. And so finally, we see that the request for a k value that gives at least one positive integer solution for x is a very specific request indeed. So how do we solve this? Well, if we look at the original equation, it should seem that we can only get positive integer solutions for x if k is also an integer. Why is this? Well, if x is a positive integer, so will be the x cubed term. And so will be the constant term of 11. The minus kx and x terms can be factorised as k into 1 minus x. And regardless of what integer we choose for k, that expression will only be an integer if k is also an integer. So even if the question hadn't told us to only go looking for integer values of k, we would already be under that constraint. And it's this realisation that helps us move to the next step. And that is to realise the expression x squared plus x plus 1 plus 12 over x minus 1 must also be an integer. Well, the first term, x squared, will already be an integer because we're already only considering integer values as possible solutions for x. The x term, of course, will also be an integer, and 1 is already an integer. And so the logic leap and the solution to the puzzle is to realize that the fraction 12 divided by x minus 1 also has to be an integer. Well, that means 12 has to be divisible by x minus 1 without remainder. Another way of saying that is x minus 1 must be a factor of 12. Well, we know what the factors of 12 are. They are 1, 2, 3, 4, 6, and 12. Solving for x gives 2, 3, 4, 5, 7, and 13, and no other numbers. And now we're getting down to the short straws. If we plug x equals 2 into the expression for k, we find that k equals 19. Interestingly, if we make x equal to 3, k is again 19. For an x value of 4, k is 25. For 5, it's 34. For 7, 59. And if x is 13, k is 184. And now we've answered the second part of the question. We're not asked to find out, of course, but there are a couple of other interesting things you can do. You can work out what is the k value and the x value for which there are exactly two solutions, or to be precise, when the two positive solutions are identical. And the question also doesn't ask us, but of course we could find all of the other roots for the equation for each integer value of k. For example, for k equals 19, we already know that x equals 2 and x equals 3 are solutions. If we multiply x minus 2 and x minus 3 together, we get x squared minus 5x plus 6. And if we divide our original cubic polynomial by this new divisor, we get a quotient of x plus 5. Well, that tells us that when k is 19, the third solution for x is x equals negative 5. Why don't you see what the solutions are for the remaining 4 positive integer values of k?